In this video, we'll be looking at trigonometric identities and how to use them to simplify expressions that have trig functions in them. The first identities that we're going to look at are the reciprocal identities. So first, let's remember what reciprocal means. Kind of the layman's term of reciprocal is the flip. So if you are taking the number 1/2 and you are taking the reciprocal of it, it becomes 2. So you flip those fractions. So if I've got 1 over the cosine of theta, well, if you remember, 1 over cosine of theta is secant of theta. So these are the reciprocal functions. Now, for me, I have a really silly way of remembering them. For secant, secant has the letters SEC, and if you know anything about college football, the SEC is the Southeastern Conference, and down in the South, they all talk like this. So what I say is the SEC is in the South, 'cause that's correct. So that's the way that I remember that relationship there. It's kind of silly, but it's helped me get through this. The next reciprocal identity is 1 over sine of theta. If you remember, 1 over sine of theta is the cosecant of theta. And I remember this because in the English language, it is a sin to not have any vowels. So this is actually the only abbreviation for a trig function that has no vowels. And this kind of looks like the word sin. Remember, it's pronounced sine, but it looks like sin. So it is a sin to not have any vowels. The last reciprocal identity is 1 over tangent of theta. And this one, not too many people mess up, but 1 over the tangent of theta is cotangent of theta. And I do have a very silly one for this one as well. If you go outside without a coat, you get a tan. Most people say if you go out without a coat, you get cold, but that's the way I remember it. Hopefully that's helped you guys remember it at least a little bit, but this is a reminder of our reciprocal identities. Now, most people, when you look at this slide, you might think, well, this is the same slide as last time. But this is the other side of it. This is the flip side of it. So if we think back to reciprocal means to flip, well, secant is already a reciprocal function. So if you reciprocal a reciprocal, if you flip a flipped thing, it goes back to normal. So 1 over secant of x is actually cosine of x. Now, if you'll notice, I changed the variable here. I changed that letter on purpose. If you're given a theta, you've got to use theta. If you're given an x, you've got to use x. As we go through math, people tend to use a lot of different variables. Yes, it's very common to use x and theta, but we can throw out a p or a q or a's or b's, whatever we want. So now we'll go through 1 over cosecant. Well, it has no vowels, and that right there is a sin. And then we've got a coat. Luckily, we've got a coat because now we won't get a tan. So the reciprocal of a reciprocal is the original back. These reciprocal identities really shouldn't be anything too new or too difficult, but it's something to kind of keep in the back of your brain. The next set of identities we're going to look at are the quotient identities. So quotient, if you think, that reminds me of division. So I've actually got a division bar set up right here. And we're going to go ahead and figure out what tangent of theta equals. Well, as you've experimented with the unit circle and the different trig functions on it, you may have discovered what tangent of theta equals already. So we'll go through tangent is the opposite over adjacent. And if we think about it, well, isn't the sine of theta opposite over hypotenuse? And isn't the cosine of theta adjacent over hypotenuse? Well, I've got a fraction inside of a fraction. So if I multiply by the reciprocal, there's the word reciprocal, it just means flip. So keep, change division to multiplication, and flip hypotenuse over adjacent. Well, these hypotenuses cancel out, and I'm left with opposite over adjacent. So what I can say is opposite over hypotenuse, well, that's the sine of theta. Adjacent over hypotenuse, that's the cosine of theta. When I divide these two, I get opposite over adjacent, which is the tangent of theta. So that right there is a little quick proof as to why the tangent of theta is equivalent to the sine of theta over the cosine of theta. Now, if we apply our reciprocal identities, the reciprocal of tangent of theta is cotangent. In this case, I changed it to an A just to keep reminding you guys that the variable itself doesn't matter. It can be any letter in the whole wide world. But the reciprocal of tangent is cotangent. Well, if I want to reciprocal the right-hand side, then it just flips the fraction. So cotangent of A is equivalent to cosine of A over the sine of A. Quotient identities aren't too terrible. If you guys think about it, really all you have to know is this piece right here, because if you know your reciprocals, you know your cotangent. The next identity is the Pythagorean identities. To get this one, we're actually going to go back to the unit circle. So I'm going to first draw just a random angle, completely random. We do not know what this terminal side is. We do not know what the actual angle is. We're just going to give it a random name, which we'll go ahead and say is theta. So this angle right here is theta. We don't know what that angle is. It looks like it might be somewhere around 60 degrees or so, but there's no guarantee. This is just theta. Now, if we think back to the unit circle, we know that we can create a right triangle. So we can split this into our x, our y, and then our hypotenuse. So I'll go ahead and tell you this is on the unit circle, so the hypotenuse is 1. Oops, still have my straight line tool on. Hypotenuse is 1. While thinking back to the unit circle, the coordinate points right here are your cosine value and your sine value. So this right triangle has this leg being the length sine of theta, and this leg being the length cosine of theta. Well, the name of this identity is Pythagorean identity. So let's go ahead and use Pythagorean theorem on this. Pythagorean theorem is where you take the legs of the right triangle. Oop, I'm going to run out of space. Is where you take the legs of the right triangle and square them and add them together. And that should equal the hypotenuse squared. Well, now I'm just going to plug in those values. One of our legs of the right triangle is cosine of theta. Another leg of the right triangle is sine of theta. And last but certainly not least, the hypotenuse is just 1. Well, cosine of theta squared, we don't write it like this. We like to put it as cosine squared theta. Plus, same thing here, we don't write it as sine of theta squared because we don't want to get confused as to where the squared goes. So we write it as sine squared theta, and 1 squared is just 1. Well, this is your Pythagorean identity. This is the first Pythagorean identity that we're going to learn. Notice I said first because this is a plural. So let's go ahead and take a look at how we can take this Pythagorean identity and discover 2 other Pythagorean identities. So I've got my Pythagorean identity written out twice. And what we're actually going to do is use all of the identities that we've seen so far. So the first thing we're going to do is, it's totally random. You get to choose. Would you like to divide by the sine of theta or the cosine of theta? Well, I have no idea what you said because obviously this is a video, so I'm going to assume you said, let's divide by sine of theta. So I'm going to take both sides and divide it by the sine squared theta. Sine squared theta. So this still keeps me balanced because I'm dividing both sides by it. But now I can split up these fractions. So sine squared theta over sine squared theta plus cosine squared theta over sine squared theta equals 1 over sine squared theta. Here's what's beautiful about this. Sine squared theta over sine squared theta cancels out to be just 1. So 1 plus, well, cosine squared theta over sine squared theta. Well, that looks a lot like a quotient identity. Cosine squared theta divided by sine squared theta is cotangent squared theta. Last but not least, 1 over sine squared theta, well, that's a reciprocal identity. It is a sin to not have any vowels. 1 over sine squared theta is cosecant squared theta. This is another Pythagorean identity. So we can take our original Pythagorean identity and use the other identities to help us create a brand new one. So this is typically what we write as the second Pythagorean identity. Oops, still have my straight line tool. Well, now we can do the exact same thing and figure out the third Pythagorean identity. Over here we divided by sine squared theta because there was no reason, that was just what we chose. So now let's divide by cosine squared theta. We'll get something slightly different, and we'll see that third Pythagorean identity. So divide both sides by cosine squared theta. And now we can split up this fraction again. Sine squared theta over cosine squared theta plus cosine squared theta over cosine squared theta equals 1 over cosine squared theta. Again, we're going to use those identities. Sine squared theta over cosine squared theta, there's a quotient identity. These two together create tangent squared theta. Plus cosine squared theta over cosine squared theta gives me just the number 1. And now we've got a reciprocal identity. 1 over cosine squared theta gives me secant squared theta. So there you have it. There are your 3 Pythagorean identities. That is actually the end of the teaching bit. Now I'm going to go through a couple of examples. So a lot of these simplifying problems, we're given a trig expression, and we're supposed to make it look nicer. And that actually happens quite a bit in physics. I can't tell you how many problems in higher level physics I've looked at and said, oh my gosh, this is disgusting. But as soon as I start applying trig identities, it becomes a lot easier. Same thing is going to happen in calculus. You're going to be given some problem, and it'll become a lot easier if you're able to identify how you can simplify it. So first thing I notice is tangent of x times cosine of x. So I can actually turn everything into sine and cosine. That is kind of my last ditch effort. If I don't know what to do, I'm just going to change everything to sine or cosine and see what happens. So tangent of x, if I'm asking myself, how can I turn this into sine or cosine? Well, I'm going to look at all of the identities that I've seen, and I can actually take the quotient identity and replace it here. So tangent of x, I know, is equivalent to sine of x over cosine of x. Now, these parentheses aren't necessary, but if they do make you feel better, you are welcome to put the parentheses around it. So I have changed tangent of x into sine of x over cosine of x. Now we'll change cosine into something with sine or cosine. Well, it's already done. There is no need to change cosine of x into anything because it is already a sine or a cosine. Now, as you look at this, some of you might notice what's about to happen, but if you don't notice what's about to happen, your instinct should tell you you've got a fraction and you've got a whole number. Well, if you want to multiply those, you should turn that whole number into a fraction. And now, as you look at it, you can say, well, hold on a second. Cosine of x, cosine of x. They cancel out, and I'm left with sine of x over 1. So all of this just becomes the sine of x. So that's what these simplifying trig expressions are meant to do. We're going to take something nasty and turn it into something that's hopefully a lot nicer. Looking over at this next one here, I'm going to go ahead and split it. This one looks a little bit more complicated because the first thing you notice is I can't change anything into sine or cosine. I can do something with these ones, but that's going to make it a lot more disgusting. The only time a 1 shows up are in those Pythagorean identities. You don't want to take a 1 and turn it into a Pythagorean identity because then you'd be adding in sine squared theta plus cosine squared theta, or in this case, b. So something in the gut, in your math gut, is probably going off. You can, if you really wanted to, distribute across, or as some people would say, FOIL. We can go ahead and distribute these guys together. Also, well, let me go ahead and do it before I give you guys the trick. So 1 times 1 is 1. 1 times positive cosine of b is positive cosine of b. negative cosine of b times 1 is negative cosine of b, and negative cosine of b times positive cosine of b is negative cosine squared b. Well, hey, positive cosine of b, negative cosine of b. It all reduces to 1 minus cosine squared b. Now here's a little shortcut that I was going to tell you. This is the expansion of difference of two squares. So difference of two squares multiplying by the conjugate. Those two are reverse actions of each other. If you recognize that you're multiplying by the conjugate, then you can jump straight into that difference of two squares. But as you see, you can just go ahead and multiply them out. So now something else in my math gut is going off. This looks really similar. Anytime I see 1 plus or minus some trig function squared, or some combination of trig functions that are squared, an alarm bell goes off telling me to look at my Pythagorean identities. So I look at my Pythagorean identities, and I see that there's a trig function that has, there's an identity that has cosine squared and 1. So I'm going to write that off to the side. Sine squared b plus cosine squared b equals 1. Now, I need to somehow find a way to rearrange this equation to make it look like this. Well, I've already got the 1 off to the right, so I'm going to subtract cosine squared b. When you subtract cosine squared b from both sides, you end up with this. Well, you've just written a statement from a totally true statement, Pythagorean identity is always true. If you subtract cosine squared b, which is a valid math move, you have discovered that 1 minus cosine squared b is equivalent to sine squared b. Well, I have 1 minus cosine squared b, so it is equivalent to sine squared b. So what I suggest students do is kind of put this off to the side and rearrange. Please don't try to just say, oh, I see a 1 and a cosine, it's probably sine squared. Because you're right, it probably is, but we'll discover it's not always. So here's the next example, and this actually is going to show us that you can't always just assume it's going to be cosine squared theta. A lot of students will look at this and say, well, it looks like Pythagorean identity, which means the answer has to be cosine squared theta, right? We're going to discover that it's not going to be cosine squared theta. So let's go ahead and do what I suggest, which is go ahead and write out that Pythagorean identity. So the Pythagorean identity you guys are looking at is sine squared theta plus cosine squared theta equals 1. Now ultimately I'm looking to rearrange it to equal sine squared theta minus 1. Something equals sine squared theta minus 1. Well, I'm going to rearrange this equation. I see sine squared theta, so I'm going to subtract 1 from both sides. Sine squared theta minus 1 plus cosine squared theta equals 0. Well, I don't have sine squared theta minus 1 on this side. I've got this plus cosine squared theta. So to remove that cosine squared theta, I need to subtract it to the other side. Sine squared theta minus 1 equals negative cosine squared theta. So this is what you've got to look out for. It's not always going to be that this Pythagorean identity gives you the other trig function. Sometimes you get the negative version of it. So here we have negative cosine squared theta as our answer. In this next example, this is one of the first ones that when I show students, they tend to say, oh, well, there's tons of different ways to do it. I can grab 3 different students and each of them is going to have a different way of solving them. I've actually waited to make this video for a very long time because there's so many different ways to look at it. That's one of the beautiful things about math is you can do tons of different things and still get the same answer. So I'm going to go through the way that I would look at it. So something in my math gut is telling me to distribute the secant of theta, because that way I can get rid of these parentheses. So I'm going to go ahead and distribute just like we did in a previous example. And I get secant squared theta, forgot the c. Secant, with a c, squared theta minus secant of theta times cosine of theta. So here, immediately, I get another alarm bell going off saying, oh, I see a squared trig function. I'm probably going to be able to use Pythagorean identity at some point, but this is not a 1, and it's not a trig function squared. Or is it? If you remember, secant of theta is 1 over cosine of theta. So 1 over cosine of theta times cosine of theta. I'm going to go ahead and write out the rest of it just so I don't get it lost. Nothing ever disappears and reappears. So 1 over cosine of theta times cosine of theta, well, isn't that just 1? Secant squared theta minus 1. Now I have a trig function squared minus 1. There's a little hint that I should probably look at my Pythagorean identities. So I look at my Pythagorean identities to see if I can find one that has secant squared theta and a 1. So this time I am not going to end up using sine squared plus cosine squared theta equals 1. Instead, I'm going to use tangent squared theta plus 1 equals secant squared theta. Well, I need to get secant squared theta minus 1, so I subtract 1 from both sides, and I discover tangent squared theta is equal to secant squared theta minus 1. I have secant squared theta minus 1, which means my answer is tangent squared theta. So follow your math gut, perform some operations, and see if you can find a way to use those Pythagorean identities. I have one more example for you guys, and it's one that makes you scared when you look at it, but I promise you it's not that bad. So here's a problem where students tend to get scared when they look at it. They see a lot of stuff going on. They see fractions, they see squareds. They just freak out. One of the things that you need to keep in mind with these trig identities when we're simplifying them is take a breath, relax. You can have your emotions. A lot of times I get scared when I look at a big math problem, but you've got to have that reaction and then say, okay, I can do this. So let's break this up. I see sine of x times cosine of x. Well, I can't think of anything to do with that. They're already in sine or cosine, and I can't multiply those together. So let's look down here. 1 minus cosine squared x. Well, hold on. We've trained for this moment. We see a trig function squared, and we see a plus or minus 1. So we're going to jump to our Pythagorean identities. And we're going to take the one that has cosine squared and 1, which is sine squared x plus cosine squared x equals 1. Now we rearrange to get 1 minus cosine squared x, so we will subtract cosine squared x from both sides. Sine squared x equals 1 minus cosine squared x. Well, now we have 1 minus cosine squared x. So 1 minus cosine squared x is equivalent to sine squared x. So that whole denominator is actually just sine squared x. Let's recopy that numerator down so we don't lose anything. Well, now at this point, we can actually cancel out this sine of x and one of these. So if you don't see it, I'm going to go ahead and write out the intermediate step here. So I tend to skip this step when I'm doing it on my own, but some of you guys it may help. Sine squared x is actually sine of x times the sine of x. Well, now it's easier to see, oh, wait a second, sine of x cancels with sine of x. Again, when I'm doing this on my own, I tend to jump straight from this step to the next step. So when I cancel out those sine of x's, I'm left with cosine of x over sine of x. Well, hang on. That right there is a quotient identity. cosine of x over sine of x gives me cotangent of x. So there it is. We've taken this super disgusting thing. We've done Pythagorean identity, and we've done canceling like we've been doing for years. And we've discovered it equals this nice, pretty cotangent of x.